good evening, everyone. Thank you for coming to the second meeting in 2 weeks of the Bay Area R user group. We are fortunate both to have speakers tonight in town that we've built this meeting around, and to be able to get a place at the last minute, especially one with as good acoustics as this. And so I want to thank the Trianon Theater people and the R Studio people and Revolution Analytics for providing the food. What we're going to have tonight is a series of talks. So there'll be a lightning talk, and then DIrk is going to do a tutorial in Rcpp, and then there'll be another series of lightning talks. The lightning talks will be 12 minutes max, within just a couple of minutes of questions while we're transitioning. And I think all the speakers will stay, so there'll be time for questions afterwards. I'll be the timekeeper, and I will give the speakers the 5-minute signal and the you're done signal. So announcements, we have a couple of announcements. We're already scheduled 2 more meetings. We have next month's meeting will be held in conjunction with the Strata conference on site at Strata. And you can find that on the website, and there is even a discount code for Strata should you want to attend the conference, but of course the meeting is open to everyone. And the following month there will be a meeting in conjunction with the Predictive Analytics World Conference, and the same deal, go to the website and you can see a discount should you want to sign up for the conference. And with that, I don't have any other announcements. Is there anyone else who'd like to say something? Well then, let's get started. Michael, please.
My name is Mikhail Kozine. Today I'm going to talk about a package that I've been writing. I just recently started writing Taylor Arnold based on a package that was written by Simon Bennett called ioregression. I'm going to talk about, so for this talk I'm going to provide an example and illustrate a numerical instability. Show that if you give up a little bit of stability, you can implement large regressions out of the board. And I'm going to introduce this ioregression package that builds, again, on IO tools, which is a package that's really fast at grabbing data from disks and turning it into data frames or names. So the other people involved are Simon Bennett and Taylor Arnold, both are taking 2 labs research. So just to start out with this is an example. I'm going to do this is an example of a regression. So I have 2 columns of data. One goes from 1 to 100. The other is also going from 1 to 100. I'm going to put a little tilt on it, and then just add a little bit of noise to it. And that's going to be my data matrix. My y is going to be the x1 plus x2 column. And if I do a solve, so basically, so if I calculate the beta coefficient for it, so basically you are solve of x transpose x times x transpose x inverse times x transpose y. You can see you get an error from QR solve because the matrix itself is singular. Now, if you reduce the tolerance to 0, you can see you can get beta coefficients, but they're off by about 2%. Essentially, they're wrong. And if I do look at the standard deviation of the residuals, they're at about 0.1. So you can compare that to something that is numerically stable, which would be just the standard deviations of these LM, which doesn't do the same matrix conversion, makes use of the UR decomposition, and the noise level is much smaller. So this first example is less numerically stable than the implementation for but the thing to think about those, why would I include x1 and x2 if they're nearly linear? So a lot of times when we're doing data analysis and we're doing regressions, we'll get coefficients. One will be significant, one will be not. Will be nearly linear. What's happening is LM is picking out one of them to regress on, and there's basically no information left to do any kind of prediction. So what I could do as an alternative is just regress onto x1. So we could solve using x1 and not my x2 column. I get a beta 2.01, and my standard deviation is somewhere between LM, which was the most numerically stable, and the numerically unstable version. So essentially, the idea is, so I'm going to do a math trick. So if you run into a really hard problem, sometimes you assume it away and show something else. So that's basically the premise for this. Numerical analysts are learning. I'm just kidding. So basically, I'm going to give up a little bit of numerical instability, and I'm going to say if I add numerical instability, it could actually have collinearity in my regression. So that may or may not seem reasonable, but the bigger question is, why would you actually do this? And the reason is that for these problems where you have a lot of samples, not many problems, it's very easy to implement this as being embarrassing in parallel. Right? So if I think of X as my data matrix, I can take continuous blocks, and block-wise, I can calculate X transpose X. And at the same time, I can block-wise calculate X transpose Y. So if my X blocks and my Y blocks are co-located, this is a completely local computation. And I can keep track of my X transpose X's, and keep track of my X transpose Y's, and then at the end, I can sum up the X transpose X's, take their inverse, and multiply them by the sum of the X transpose Y's. So again, the benefit then is this becomes an embarrassingly parallel problem. So this is one part. This is basically the numerical assumption, or the kind of the methodological assumptions for the talk. The other more practical issue is that a lot of times when we're doing data-intensive computations on a lot of data, we spend a lot of time the most time doing I/O, basically grabbing things from disk, especially in R, reading into a data frame, which can take a long time. And it's not because read CSV is working poorly or anything like that. It's actually that read CSV is very robust. But if you can provide a little bit of information, you can read the data a little bit, in a little bit different way, you can do things a lot more quickly. The other thing is after you read the read CSV, that's not a representation that's amenable to actually doing the regression. Right? You still have to transform into a model or design matrix. So there's actually a lot that goes into going from disk to analysis, or at least part of an analysis. So to handle the I/O problem, there's I/O tools. So as an example, I'm just going to start running this. And I'm going to come right back to it and explain it while it's actually running. And it looks like it's running. All right, so what I'm going to do is basically, I'm going to load the I/O tools library. I'm going to specify and this is the airline data set. So this is the 2009 Data Expo Challenge. It's about 120 million rows. It's all airline flights, all domestic airline flights from like 80 something through 2008. So I'm going to specify the common classes, and after that I'm going to use I/O tools to basically slurp in airline.csv chunks, a chunk at a time. And with that I'm going to use something called DIrk split, which is going to turn this chunk into from a binary representation into directly into a data frame. I'm just going to grab the number of rows, and I'm going to return this as a list. So the thing that gets returned then is the number of rows for each one of these chunks. So they're actually going to be all about the same, probably except for the last one. And then I'm going to add them up just to tell you the total number of rows. So you can see to go through this is 12 gigabytes of data. It took 42 seconds to get the number of rows. You can see when I do this, add up all the number of rows from my return, that is the exact number of rows in the CSV. There's one line for a header. Again, it took 42 seconds. If you were to do wc-l, which is the Unix command line to tell you how many lines are in it, it takes about half the time. But if you think about what's actually happening, is all WC has to do is open up the file and start looking for end-of-line characters. Here, we're actually taking these chunks, we're turning them into data frames with the specified column types, and we're getting the rows on. We're getting the types of rows. So you're going to pay for time. You can think of, you can think about half that as the lower bound, which you probably could do in C. So the other thing you can do, I'm going to skip this. So that was IO tools. This is so the other thing you can do is actual regressions. So this is the second example. I'm going to fill in the actual column names. After that, I'm going to do a little bit of cleanup. If I see that I'm on the first row of the airline data set, I'm just going to remove it. And after that, I'm going to call ioLM, so that's the IO linear model function. And I'm going to do the regression departure delay, arrival delay regress onto departure delay. IO regression it takes files or connections. So in this case, I'm actually doing a regression directly on a bzip file, and I'm doing this data frame, this pre-processing on it. Now, the thing that's returned is actually a little bit different than a regular LM object. So we're not doing things like keeping all the residuals because it's silly for data set size. And the other thing is, if you want to do the summary, there are extra summary statistics that are calculated that are calculated after you get after you have the model. So the summary for ioLM is a little bit different in that you have to specify the file that you want the summary on and in the pre-processing. So that's still running in this time, probably 2 minutes. Okay, 2 minutes. So there's another example that I'm not going to run right now that goes through the entire airline data set and does this regression of departure time, total day of week plus that should be arrival time. Day of week departure time. I'm doing a little extra fiddling because this departure time is it's formatting is really easy, so I have an extra function to do this to do the extra pre-processing. All right. So the return here's the return from my linear model. You can see and basically we just hijacked summary.lm. So we took the regular LM objects summary and filled in the list elements that it needs. Again, except for the residuals, that's why they're names. You can see you can see the model diagnostics, also the absurdity of applying traditional model diagnostics using a linear model, but it is there. All right, so the current status is it's under heavy development, but there's an initial version for OOS. It turns out that the Lars package is really amenable to plugging in IO tools because it's using the X transpose X and X transpose Y. The GLM is coming next. You next have coming in. Right now it's working. The demo that I showed is using IO tools, but there's a distributed system called Rcpp that Simon Organic has been working on. It basically works on top of Hadoop. And there will be integration for that also. If you want to know, this is where this is the location for the package. If people want to download it and send forward ask questions, it's great. Thank you.
So while Dirk is setting up, there's time for a question, I guess.
Are those beta coefficients going to still be blue and all that? That doesn't change any of that.
Sorry, can you
Are the coefficients going to be the best linear unbiased estimates? That they always talk about. That's all.
Yes.
None of that's changed by any.
Yeah, so mathematically they're correct. The different it is a matter of floating point precision. If you have this example like the one that I showed you at the beginning. Oh, so sorry, then what happens, what happens is if you're calculating x transpose x and you have a collinearity, what happens is it's detected. So I do a Koleski decomposition on x transpose x, figure out which one of the variables are collinear, and then remove the ones that are collinear and give you the result, along with a warning just to let you know that they're not in one direction.
This does that automatically?
Yes, yeah.
Thank you, Mark. Well, there.
Good evening, thanks for coming. Thanks so much to Joe for setting this up on using short notice. I mean, I was in town just like right before short workshops, so let's do it. I think initially it's at 16 minutes. I may have less material because the full blown tutorial will have to go 3 hours, 6 hours. But so quick show of hands. I mean, did you use Allstate before, or you know, like, so who has used it before? That's good. It's not too many of you because I mean, typical introduction. Who has ever used it? And keep the hands up. Is interested in it? Good. Now then we're right in time. So I mean, there's lots of material on my website and other stuff. So with that sort of motivation, why are we doing this? This is an old tweet which I saved from a couple of years ago from some of the folks at Harvard who worked with IQSS there. People like it because it makes code reasonably clean and clear, but gets a lot faster. So it's a bit like R, better. So my face remains down there as two drivers of it, and likewise. This is another tweet from someone a little while ago. Love that almost every time I rewrite code in it, holy shit, that's fast. And I'm unapologetic for it. So it does a lot of things well, but if it only did things faster, that would actually be fine with me too. But it does sort of do more things. So I was thinking, I have to apologize. I ran out of time, so it's not an entirely new presentation, but I was thinking I should have a punny title to borrow from that reasonably famous book about JavaScript, The Good Parts. And I figured I could talk about Rcpp, the good parts. Because there's clearly things that are very good, and there's some that are not so good. What's not so good is that when you get error message, you get error message from C++ compilers, which can be incomprehensible and go on for pages and pages. Some of the stuff is new. You have mental nodes which is going from one language to the other. But I think on balance it's still sort of all worth it. So I don't really have full exposition, but I have to sort of work on it. But I think ease of use is key. And I have some examples for that. Over the passage that Rcpp had since we sort of resurrected it in 2008, the use has gotten much better. If you've seen me present or seen old slides years ago, we did all of this with a package called inline. That was already not so bad, but now it's much better. This is only possible really because we have R as an ecosystem around us, and R takes care of compiler, linkers, options, abstracts the operating system away, and we essentially from the package just have R command compile, R command champion, call for us, and that just works reliably. So R as a build system really isn't so bad. I'll have a little example for going from R to C++, and our claim is that really isn't that large a distance, and something that I should expand upon that I thought I could get to sort of early back, what I've done in the last year in terms of new packages, small ones, large ones, stuff at work, and more or less how to use C++ as a glue language, or help with Rcpp as a glue between things that exist in C++ or C and are good to use and I want access to in R. And because of the ease of use and the closed object model, the passage from R to C++ in that is really pretty seamless. You can have this as a glue and just bind things together. So I'm getting a lot of fun out of maybe to registry libraries. I've read a short Python library from years and years that a guy put up, and that was sort of a morning's work for a package. It all works quite well. But that's the talk I could have given with more time, but we don't try. But to situate this, Rcpp is an extension for R, so I'd like to sort of recap why we're using R and what's good about R. We work interactively, we can explore data, visualize data, seeing things is really important. It's really good to access, retrieve, or generate data. There's basically not a backend system that you can't talk to from R these days, and there's not a way to summarize things. I mean, we're doing tremendous things these days with Litter and Speed and JavaScript wrappers for interactive reports. So R is a really good middleman for working with data, so which I don't like it as an environment. And R, of course, has always been extensible. It's written largely in C and in R, and how to work with it from C is described pretty well in writing our extensions, even though the manual isn't always the clearest or most linear to jump into different chapters. There's of course a lot of fortune in there because many of the linear algebra basics, things like R and other systems use R and Fortran. Simon gave us R-Java a couple of years ago, and there had been support for C++ from the very beginning. There's on a deprecated directory somewhere on prem is still an example from 2000, but that basically really worked the way you loaded C. So it always worked, but it was a bit tedious. So then the question is, okay, so you told us you like to use R, you like to extend R. Now why do you extend the C++? And if you just punch Y C++ into Google, they pull their result sets every now and then, but I did it once and I got 28 million, and then I got 42. I think it actually went down before we did 20. There's lots. I mean, there's obviously lots of pages that talk about C++ and make a great case for it. Wikipedia, as always, has a very comprehensive, if hard to swallow definition. It's statically typed, so that's different from R. You declare a type of a variable and then on its states. It doesn't alter. It's free form, multi-paradigms, you can do different things different ways. It's definitely compiled, there's always a compilation step. We need to go into object or do the thing. General purpose, you can do anything with it, like say Python, and it's very powerful. It's industrial strength, it's vendor independent, that's quite important to some, so it just can't go away. Very widely used and still evolving. I first put these bullet points in slides, I think, before the C++ 11 standard was passed, but with what happened to the landscape with Java, C#, other languages, C++ got a little bit of fire on its neck, and it has evolved too. It's super widely used in science and research. If there's something that you can connect to, there's probably a C++ API, and there's DC2. Another reason why C++, so a bunch of books from which I learned, which are recommended to people, are these by Scott Myers. He has effective C++ and more effective C++. Those are basically topical little stories, very short, 3-4 pages. And the first one, effective C++, starts with what is C++? And he says it's a federation of languages. It's really a superset of 4 different ones. You don't have to master all of them. You don't always have to stick with one paradigm. You can mix them freely, and you can easily just use some of them. I've been sort of self-taught. I got into this as a grad student. I learned some C as an undergrad. And I was joking when we were grad school years that I was actually using C++. I was not using C++, because I wasn't using all the features. I was just using some basics. And that's sort of just fine. It got a lot of steam and got where it is today because it extends C, so it could be used where C was. It brought a lot of object orientation. Templates are definitely new and novel that other languages don't have. STL is something that was contributed outside of Ballad and the language core, but it got eventually moved in. Those are all 4 points being made by Myers that are there. And these days you can say that C++ 11, C++ 14 had enough features to be called a fifth react, to sort of paraphrase a little bit what he said. Advantages and real uses. So it's a super mature language. We don't have too many obscure sort of design issues there. Most of the rewards are sort of known. It's a very strong performance focus. There's a dictum that says if there are features in the language that you do not use, you don't pay performance penalty for it. That's sort of different from Java and C#. There's no JVM on Java here. We had a C++ standards community in Chicago where I live 1.5 years ago, and Myers and Structure actually gave a joint talk. And Structure was doing this. Why is there this performance game? Why does it matter? And we're waving a cell phone around. because these days you're not just looking for native performance, you're also looking at performance per watt. And if you don't have to waste energy on things that don't add anything to your program, you just basically get further. Also, there's enough for low-level abstraction down to the machine that you don't really need an intermediate lower level there. You leave no room to the machine in C++. So it does that. It's low level, yet at the same time it can be very high level and abstract. And C++ we definitely do more things that come from functional languages. And as I said, it gets extended. And while there are complex things behind it, you don't really have to worry about these using Rcpp. This was fun too. So actually, just about the last time I was involved a couple of years ago helping with the summer of code. I came to the sort of wrap-up meetings and talk at Google and spent the afternoon with John Chambers leading up to that. And he reminded us of that. I think that was 2010. He had just given a talk in Stanford. That's the part that had done this one out. This is sort of a napkin drawing this is actually quite impressive, from 76. That's sort of May 5th. That's before S was born. It's still called the language, I think the interface language or something. And this is sort of a drawing of how there's inner compute cores, ABC in the server, wrapped in outer subroutines. Some sketches about how you get variables in and out, how you call it, how the memory layout works. And John's point basically is that a very long time ago, there was a vision for having trusted compute algorithms at the core, and pretty seamless interface of what you compute there to the environment in which you work, which for us now is R interaction. Now we can go from R objects that can have a list, a matrix, a data frame, basically pass it down in C++, and because we can do some magic in template, have it right there. So it fulfills a really old, long vision from Bell Labs. So some more bullet points on what the drawings are. It shows sort of trusted numerical libraries, which of course 70s, right? At the time, were mostly written in Fortran. Provide an environment which statisticians could use them more easily, which at the time meant writing out of Fortran files. Go from there to interactivity, iterative data exploration, which is what we have now, and make it extensible for research. All that is also written up quite well with the mission directive dictates in 2008. Last book. So I really like writing with R because it's sort of the best of two worlds. We have compiled code that goes reasonably fast, it goes to underlying libraries, C, Fortran, which gives us good high performance. And Michael was showing, with the preceding talk about how we get into stream data, what it was benchmarking it against was LL and fit, they go straight up to LabPack, we have multiple cores immediately, so you get high performance stuff. But it's also interpreted code, you can do all these tricks of working on the language, have expressions, and so on, which is good for research, experimental, and prototype. So what did we get then with Rcpp use? It's pretty easy to learn. Doing simple first steps is not that hard. I'll show you a simple real example in a minute. But it's easy to use. I alluded to that earlier because R gives us a stable and easy to deploy build environment. It's expressive. We put some things into C++ that you don't have in other C++ environments, so we're playing a little bit with vectorized expression. It's seamless. You can pass vectors, matrices, lists, as 3 objects, as 4 objects, reference points, running functions up and down is good. Makes things faster, and it's extensible. You can bind to other things. So, and where does it sort of fit in? If you didn't have Rcpp writing directly at the C level, this is the interface that you have. From the R level, and you can do that. This is basically what's in the innards of many packages, so you can do it at the prompt directly. There's a function called .call. It's preferable to a predecessor function .c because it has a higher level interface. .call allows you to send full R objects down rather than just things that are an int pointer and the length of that vector. And on the C++ things, you always just see these as expression objects, those are union types. It's an old C programming trick that if you try pre-C++ OO programming in C, you may have seen that. It's a union of different types, of which one at any point in time is active, and so that bit mask. Details that don't really matter. Everything is an SAXT, whether it may be a matrix or a list of a vector, and you return one of those and get 0, 1 on several of those functions down. Now, how does that work from Rcpp? And I used to go through sort of simple standard example, build it up, and then at some point I kind of said, chuck this. Because these days, most of us actually just sit straight in RStudio. So what do you do in RStudio? You just go File, New File. It offers C++ file. You hit that, and you basically get this page. Or I should say, you used to get this page. You may still do it with the release version, but I work on the nightly builds, the pre-release versions that are about to come out with the new one. There's a couple of other nice distinguished those. So this one basically is all that's there, and that's already written for you. This is a full, complete file. Things that matter is a single header file. So instead of having a barrage of header files, we have one that pulls in the other one. So you just need a single file, rcpp.h. Then there's a shortcut notation to opening a namespace. It's a little bit how namespaces work in R, that if you declare that rcpp, oh, that's a nice typo, I never noticed that. No, right, no, that's right, rcpp. Getting blinded by being too close to it. So then you don't have to prefix all the objects in the namespace explicitly with the namespace of a colon mark. A little bit of explanation and pointers to further help. A tag, an attribute as we call it, as a comment. This is taken up as a regex, so it's important that it's 2 square brackets on each side, no spaces in between. This basically tells the build system that comes with Rcpp to take this function and make it callable from R. And that's all we have to say. If we want it internally, we have a function not exported to R, we just take this line out or break the regex. So sometimes I just put spaces between the square brackets, and it's not exported. We sometimes do that because we don't want the function there already, but this now says we want a function that takes an int, multiplies the int, and returns it. That's all you have to do. If you've ever tried to do compile code in something like MATLAB or Python, it's a lot more labor, or in R without this framework, with the older with basically the functions that I showed you before. What has changed now is basically it's the same thing. It's still a ×2 vector, but JJ and I sort of chatted about this and realized we don't actually have to show that with a scalar because, as you may know, in R there's no notion of a scalar. Everything really is a vector. You may just have vectors of length 1, so we may as well define this interface that way. So this always works straight on the vector. So you can send in the vector sequence 1 to 9 and run the square root of it and then multiply that by 2, and it will operate in once on the vector by taking the vector, multiplying the vector by 2, and returning the double elements. You don't have to unroot this by hand. If you're then in RStudio, you press a single button, it compiles as the function there, and you can call it. So that can be that simple. That, of course, assumes that we have a system with the compiler, which on Windows requires an additional installation, but it's nothing more than you need to do with R otherwise to compile packages. On a Linux box, it just works on a Mac, Xcode, and all that sort of stuff. No additional commands being put in from Rcpp. So that just works, and those files you don't even have to write. They come with a push button from Rcpp. This ease of use aspect from Rcpp, there's really 3 functions that work for you. The very simplest that we have is evaluation of a single expression. You can always do something like this just to test whether your build system is set up right. So here, it would take the 2 plus 2, and of course, no kidding, right? We all know what the answer should be. But it will take this, turn it into a compilable unit, have it compiled, load it, evaluate it as a compiled C++ program, and that way bring the answer back to you. And if your build system is set up right, you have a compiler in your class, then you get the answer 4 back, and that will have been computed from a minimal C++ function constructed straight from that expression. You can use that to extract values out of header files for testing. So Rcpp is good just for simple validation. Closely related is a helper function that takes just a text string. So what we have from this apostrophe to the beginning apostrophe, R just sees a string. The string is now sent down into a file. The include rcpp.h is put in front of it, some other stuff is put behind it, and an entire file is made out of this that creates us a function submitted as a string, and it's smart enough to basically parse that string and see what identifier we're desiring here. So at the C++ level, we're saying we want the function square. It now gives us an R function with the same name calling the code behind this. So you hit return here, same as here. It's not immediate, it takes a short moment, a fraction of a second, and you sort of notice the prompt doesn't immediately come back. Then you have a new prompt, and then you can call the function square, and it computes the square of the number you have sent. I've sent an explicit integer there calling it 7L. And then just for reasons with Nitter that I didn't want to fight, I didn't show the third one. So the simplest one just takes an expression. The next, more complex, useful ones for quick experimentation. Sometimes use that to show something on the mailing list or something's done, or have a question and say, overflow solution, which is pretty widely used. What one can use much more often is source-cpp, which will take a complete C++ file, like the ones that I showed you on the two preceding pages, and turn that into something called. You do that when you're working on a single file, a short little snippet that you test. I don't recommend that you use that for real code. For real code, you should always use packages. Now I get to how you're using Rcpp in the context of packages also in the moment. Now I have a real example that's sort of close enough from my field. I'm by training in nutrition, that's sort of a mix of statistics and economics. And this was an example that got sent to me from a young professor in Kansas who used that on his, I think, master's thesis in econometrics. It's about simulating what's called a vector autoregression through, in the simplest case, it's two columns of variables, two vectors, and it's an autoregression because each element t, the t's row, is a function of the preceding row. And because it's a system of two variables, there's a cross regression there, it means you can't generate this data and vectorize this expression. Which means you have to generate the data in a loop. Which means in R, it takes a moment. Because vectorizing is much faster than loops, but we don't like loops. So this is how you would do it in R. So we prefix it rsim, and we're having a vector of coefficients b. We, in this particular case, have assumed that our error terms have already been computed. You do this when you study certain estimation algorithms and their properties under certain error conditions. So that's why it may make sense to assume the error is given. And then we're just saying this is a problem of dimension n and k. So we're pre-filling a matrix with zeros from n to k. The first row doesn't have any predecessors, so it sticks with the zeros, but from the second to the last, we can define each row as the preceding row vector multiplied with the coefficients. That's now a generates a new row. This is a 2 by 1. Here's a thing on this, just a perfectly vector.
Just one column, right? E.
Yeah. And E, exactly. E is an error matrix of 2 columns. So at a fuller example, so I think I draw 10,000 to stick it in 2 vectors of 5,000 because it's a 5-variable system. So we're generating both columns, the rth row of R. And that then just runs, and if you're estimating the properties, studying the properties of an estimated device relation, you have to do it over and over and over, so it's not as fast as you would like. See again what we're doing here. We're picking out dimensions n and k as a function of the dimensions of the error matrix. To pick it up from that, we set up with that dimension an X matrix, we go over it and return it. In C++, it's exactly the same thing. The way I've written it here is using C++ function rather than the source CPP, and I'm doing one additional step. that I'm going to an external dependency. There's a linear algebra package that I use a lot for these type of things, and otherwise it's the same. We're sticking in B and E as in the preceding case, but now we're in a compiled language with static types, so we have to say this is now an Amadeo matrix. This used to be less performant, but these days we can properly do that as you would do that with other C++ things. It's const and a reference, so that's the most efficient way to pass things down. It's just a technical detail, but we have this sorted out, whereas earliest versions didn't have it. Then we do exactly what the R version did. We're picking out what n and k are as a function of the error matrix that's being put in. We're allocating a matrix of zeros of an Amadeo matrix type. Default is then double of size n by k. In C and C++, we're zero index rather than one index. So our second row starts at the index of 1, and we're going to less than n rather than equal to n. In other words, it's the same thing. The r's row is the r minus 1th row times the coefficient matrix B plus the r's row of the error. And now we have our simulation function. And for the build of ease of use, we're just saying to get these Amadeo things, just depend on the package Rcpp Amadeo, which for all intents and purposes just brings a couple of headers to your system where are the nodes that define that. Actually, the earlier point of the build system is just talking. And then you can just do this. So here now oh, so much for my consistency in presentation. So what was B on the preceding slides is now A. I guess I should fix that one day. And my coefficient matrix is 1/2 on the diagonal and 1/10 on the off diagonal. And I turned it into a 2x2. E is my error matrix, 10,000s, 2 columns of 5,000 each. And I'm quickly asserting that the result that I'm getting via C++ is exactly the same as what I'm getting via R. That's a good test, that you actually check that your results pan out. And because we're not drawing the errors twice, only once and reusing in both cases, the result really better be the same or you have a bug. And once that's the case, then we concern ourselves with the little things like checking out how quick that is. For that, there's a lot of useful helper packages on-prem. Here I use an older one called benchmark. You just stick in one expression and another expression. It then times those. I say that I want the results in relative order, and I only want the first 4 columns. The 5th, 6th, and 7th is other minor system time, user time things as you would get them back from the time command. And relative order just means that the shorter one is normalized to a value of 1. In this particular case, 100, and if I don't say how many, it always does 100. So 100 of these simulations over 5,000 rows is 44 milliseconds with the compiled code, whereas it is 2.5 seconds for the 100 in R. So we get a speed of about 64, basically no effort, because the program really looks the way the previous one. So that's a live example, that's not made up. So it's usually old, we used it a few times, but it's pretty easy. And I have way more examples in other longer presentations, and I'll give you pointers to where other more documentation with the very things. So I did tell you ease of use. I showed you the val CDP function, and source CDP. Because source CDP works so well, people often stick with it and use it. Don't. As soon as you have a bit more code and you want to deploy it, use a package. I mean, actually, that's the gospel and irrespective of Rcpp. You should always write the code up in a package, because a package allows you to test things, have documentation around it, have a version and a bundle. I showed you how easy it is to get a single function written with the help of Australian generators. It's basically the same with the package. So you just go in and I think it's file new project or tools new project. But basically, you go in, create package, and in the type here, the default is a straight up package. If you click on it, you get a second alternative, and it's a package with Rcpp. And RStudio will have created everything for you to make the package work. No excuses. It's not any hard. Write a package. Read. It's real things. So, key features about using Rcpp, what I really like. there are no local issues. If you want to work with compiled code on an R system, you have to get yourself a compiler. On Windows, say we don't have a compiler natively given. You need a compiler anywhere when you compile C code, you don't need anything extra to use Rcpp. So the build system really is just R and it's standard tools. There's no operating system dependency. Everything that I showed you will work on a Mac, on a Windows box, and a Linux box the exact same way. There's no passive. It's just one of the things where R is really, really strong. It all behaves the same consistently. No issues about memory management. Did I ever say pointers? Did I ever say sacral? No, these things just work. And it doesn't have to be complicated. I mean, I just showed you a little example that looped and iterated, and that's all other things we did. You can go from these one-liners, CPP function, to package creation pretty easily. Then I like to show off every now and then. So in late 2008, I started reworking Rcpp, which had been sort of abandoned. And I didn't keep track of it. And the growth in the beginning was a little slow. And then in the beginning, sort of around 2012, we had maybe 40 packages using it. I used to count every now and then how many there were, which is why these observations are a little sporadic. And at some point, we crossed 100, it became a little more, and eventually I wrote myself a script to write that down, just dump it in our data file. And I sometimes get asked when I show that chart, whatever happened there. I have a famous idea. I had been giving tutorials about it before. I had been on French for a while, and we hadn't hidden it, but all of a sudden we got ourselves a different scope. And I think when did I first show this? I may only have prepared this for the keynote as useR last year, and then I had 2 slides back to back because I showed the numbers, but then I also, how did I do this? I think after I did all this scripting, I always also wrote down what the current number of packages is. That's just the number of rows that you get back from available packages. So I have the percentage rows, because at some point I was wondering how many packages actually now use it. And it's kind of cool. It's now more than 1 in 20. What I still haven't figured out is what the total census of packages is on a track that actually have a source directory, i.e. how many packages have compiled code, and what percentage of those now use Rcpp. But it's gotten quite pervasive. I mean, it just helps. It doesn't get too much in your way. People tend to use it. And of course, the nice feature of it is if you have a particular question on how on earth would I do this or that, it helps to just look at track and look at the existing packages, because we have obvious worked testing examples. These things all do that. It's open code, you can extract it. So for hints, for clues, for best practices. And then with that, just some quick pointers for further documentation. There's quite a bit of PDF documentation in the package itself. Some of these vignettes became papers. The ones for Rcpp and the other really hardware package called Eigen, so the binding is an Rcpp Eigen and JSS. For Rcpp Armadillo, I did one with the Armadillo also and CSDK. We have a mailing list, which is pretty low volume, low nonsense, quite helpful. A couple of truthful people just lurk and help. I answer questions from Stack Overflow 2 on this. I've briefly does it earlier, and there's now 670 of it, and there's blog posts going around. There are some of mine, some of other people's. Another thing that came thanks to an initiative by JJ, we have a website that we call the Rcpp Gallery. It's just basically a bunch of markdown by the magic of Jekyll and Nitter behind it that goes over particular topics. It's sort of 2-3 screenfuls and explains certain things. So that's very good because it's also searchable. And they're all working compiled, so that's quite good. And the URL for that is gallery.rcpp.org. Hangs straight off GitHub, so it's just a GitHub Pages application. And I published some of the vignettes into a book, which you can get from Amazon on a usual basis. And that's all that I have. I guess, same to you. I mean,
yes.
Saturday night. Stick around. We'll have a great show tonight, so I'll be here for questions later. If you have questions now, we take them.
How can you include external libraries, for example, for themes, like the CUDA library?
Yep. That's why I made sort of glue code, and I have some examples for that. It depends a bit on what you have on the system. Like these 300 plus examples work. So sometimes I've written little configure snippets that just find them. Sometimes you have to, there's sort of two levels. On the Unix system, you can do it that way. On Windows, you actually have to work with the client people to have that it's there. A working example, for example, is the GSL. For many of these libraries, these are package-config, or the tools have a name of the tool -config tool. So you can, on the shell, invoke GSL-config and ask it where are your headers, where are your libraries. I do that then in the make files, point to it, because then you have a build system. These things become a bit harder to generalize because of the linking stuff, but it's been done all the time, and that's really something that I like for the glue code. What's even easier, and I didn't stress that, is, I mean, if you're a bit familiar with C++, instead of libraries, you can also use header-based stuff, templates, and then you just have to point to the header, so you can just stick them in your package, and you're basically done. You set a capital -I about where to find them, and that's then all the dependencies that you need to compile six. So it works, but at that point you get a little more OS specific, because you have to sort of do certain OS tricks maybe to find where the libraries are. If of course you're just doing it for personal use or as a user solution, you can just hardcode it. Other questions now? Otherwise later?
Thank you. Mikhail, you're next. Bryan, you're up.
All right, thanks, Joe. Awesome, Dirk. Hello, everybody. I'm Bryan Lewis. I'll talk about something that's pretty new. It's all very new, hot off the press. It's a package and an ecosystem around it called htmlwidgets. The point of it is to integrate web presentation technologies and R in a really nice, neat, tight, and elegant way. It was written by Ryan up in McGill. Sorry? Oh, he's here now. He moved. Oh, okay. I didn't realize. Sorry. So it's pretty weird. Sorry. Yeah. Okay. And I didn't know that. Thanks. Yeah. And JJ, of course. So two rock stars with this package, and then a whole bunch of us have been wasting all our free time working on ancillary packages to support the use htmlwidgets. So the coolest thing about this package is that you can use it all over the place. If you happen to be using RStudio, as you might imagine from JJ's involvement, it's really seamlessly integrated into RStudio. These things that I'm going to show you will just look like ordinary R plots. You can also use it in meetup documents, like the one we're looking at now, although it's a little glitchy. So it's pretty new, so we're going to encounter a few glitches. I should use sliding. I'm using io-slides, and there's glitches with io-slides because it's so fancy. You can use them inside Shiny apps, of course, and if you don't have any of that stuff, you can use all this just in command line on any platform. It just works. It'll pop up in web browsers. So, all of us are folks might be wondering why we would want to use these web technologies. And there are a bunch of answers to that question. The first is that web visualization technologies are really pervasive. They're used in our phones. They're on very high-performance web rendering engines and on every computer system platform. Another important reason is that there are herds of developers working on this stuff. And of course, the development is of variable quality, but some of the stuff is incredibly first rate, like Mike Bostock's D3 library and Mr. Duke's 3JS library, for example. Those are two that you'll see used heavily tonight in a couple of examples. All of these technologies are portable because these rendering engines are available and highly tuned on every platform. And some of the stuff is just mind-blowingly cool. I hope that you think that is too. I certainly think it's really cool. So rather than just talk about it, let's look at a few examples of what you can do. The first example, this is something that I worked on. 3JS is written by Mr. Duke. It's a beautiful way to hook accelerated OpenGL graphics via WebGL into web rendering technologies. And the 3JS package is a package that uses htmlwidgets to put all of that, to cram all of that technology into R. And there are a bunch of plotting functions in it. The first one is something that I needed for my own work, and that was just a nice 3D equivalent of the scatterplot 3D function that many of you may have used. And so here's a couple of lines of R code. This is actually an example from the scatterplot 3D package. But when you run that in R, you get this type of a plot, which is rendered using WebGL. So I'm actually running this all on a real wimpy Chromebook, but it works really nicely. And if you run it on a machine with a real NVIDIA graphics card or something like that, you can push this really far. I can on a desktop machine with an NVIDIA card, you can display point cloud scatter plots with like 1 million points and just spin them around, and it works really nicely. And the syntax, the grammar of this calling function is just like scatterplot 3D, so it's pretty easy to use. There's another, so that's actually a useful thing. Then just for glitz, oops, wrong way. So this, for those of you, there's few of you here that know me, it's really weird for me to be getting graphics stuff, right? It's like the first time I've ever done anything on like graphics, but it's pretty cool. So this is just really glitzy. It's kind of maybe a little bit goofy. This is one of the glitchy ones. This is the slide package. There we go. So a couple of lines of R code. Let's just plot R plots over slopes, which is really neat. And right, all those plots all have the same. Can you see that? It's a little dark, isn't it? It's really nice looking on my computer. But you can plot things with different colors, and the globe itself can be plotted either in R, or you can use an image. It has to be a flat array, every rectangular projection map. But those are widely available for most planetary bodies. And so this is kind of a neat way, like kind of glitzy way to plot some data on globes. There's another globe plotting function that, for the sake of variety, I thought I would show actually inside of RStudio. So here's an RStudio session, and just to show you that this stuff works just like R plots in RStudio, I just issued a command, and there indeed is a scatterplot 3D plot. Before you couldn't do this directly inside of RStudio, so this is kind of cool. And then here's a different kind of plot. There we go. You can also plot these types. This is going to take a moment because I have a cracked computer. Come on. Sorry. There we go. So these are kind of arc plots that are like people who seem to plot Twitter things love to make plots like this. It's just kind of glitzy, and it struggles a little bit on the Chromebook, but this is a plot of the same ASA airline data that Mike was using. That they're from and to things just for the year 2008. That's kind of neat, this is North American airline flights there, you can see that on. So I worked on this package, and I also worked on another package, which I'll show you here, along with Christopher, his last name, and JJ. This is timing Bostock's, some of the network visualizations of Mike Bostock's D3 package. I'll explain why these glitches are happening. I have slides in a moment. There we go. So you can get these nice kind of force-directed graphs this could be in your R session, or they're very interactive, right? You can do all kinds of cool, goofy things like you've seen. This is a plot of the entries of the characters in the useR. You've probably seen something like this before from E3, and now you can do this inside of your R session, play around with it. It's actually a very useful way to plot network data. And this is just one of the graph plotting functions in this package. There's a ton of them. You can plot trees and all kinds of cool graphs using that package. That one is on GitHub. I'm going to give you a link in a moment. Leaflet is awesome. Leaflet is, so 2 lines of R code. That's it. This is using the gritter to kind of compose things. Let's see. And you get that, right? This in your R session. It's pretty crazy. This should be San Jose. And you can do stuff like this. It's pretty freaking wild. I'd like to see you do this in Julia with people. Look at that, right? You can do this in your R session, in your Shiny apps, wherever you want. In a document like we're looking at here, it's pretty wild, actually, pretty cool. And then using the Hadley's kind of pipelining syntax, you can overlay other features on top of these geospatial data sets. So you can put points on there and connect things with lines, and do all kinds of overlays on top of the raw map data. It's really nifty. So check out these. Okay, one more example. Let's see. Digraphs. Yeah, digraphs is actually really neat. I have to refresh this. So the reason I'm having to refresh IO slides is there's some sort of incompatibility with leaflet and IO slides that I discovered this morning preparing this. The digraphs is a really nice time series plotting tool. You can plot multivariate kind of scatter plot and line plot time series, and it's very nicely interactive. You see I'm highlighting, picking out points that are changing on the graph. I can use sliders to look at different sliders will zoom in and zoom out of this time series plot. You know, all kinds of really neat things. You can have scrolling time series plots. Again, all inside of any R session, just like any normal R plot. It's really cool. Okay, so just a few more words. How do these things work? How does one write an HTML widget? It's really easy because the package that Renoff and JJ worked on so hard specifies a very simple, clean, and straightforward framework to implement these visualizations. All you need are 3 JavaScript functions on the HTML JavaScript side to tie a step into your R code, an initialize function, a function that handles resizing events, and a rendering function that actually plots data. You only need to invoke to connect that with one R function to make your plot on the R side. And there's a couple of boilerplate supporting functions for Shiny apps that they all are one-liners, they're very easy, and they all look the same in your package, so you just copy that. And the mechanism of communication between R and the HTML JavaScript visualization side of things is JSON. That can get a little bit heavy if you're plotting like a million points on a scatter plot, so we're thinking about ways to binarize that interface. But the point is that with very little effort, you can glue your favorite JavaScript visualization code into R now and make it behave like a normal R plot. It's really easy, so you all should write your own. It's really cool. More information is right here, including links to all of the packages on GitHub. A few of them are on-prem now. All of them will be on-prem within a couple of weeks. And hopefully some of you will contribute some cool visualizations too. Thanks.
Any questions while we're setting up?
Good.
Great.
So I will talk about a proof of concept project that we at Allstate insurance plan together with SkyTree. And it's a joint communication with SkyTree. And let me start with explaining what this project was about. It's not for advertising purposes, it's just explaining why we do that. So we are a quantitative research analytics department in Allstate Insurance. This is the largest public private line insurance company in the US. And we have a lot of data on our customers. Right? We have 20 million customers, and we have really lots of data, hundreds of terabytes in our R&D Hadoop clusters, and our analytics development is primarily our Python, and we, lots of our applications. Some of them are listed here. It's potential analysis, price optimization, streaming vehicle data analytics, and media mix models. So other than just data on our customers, we have data from the vehicles that constantly stream to our service.
And what we're interested in the tools that help us to process these data really quickly. Why? Because if you work with a really large data set, and the difference between building a model in several days and building a model in 1 hour can be so huge that you can really rethink the total strategy of your project. And it's a big deal. So 3 things that we are looking at when we're choosing these the tools that can help us is scalability, is complexity in terms of the analytical approaches, and the speed. And SkyTree provides one of these tools. I'm not saying that it's the only product on the market, but it's definitely here in terms of scalability. In terms of scalability and in terms of the analytic complexity, it really reflects what we need in this situation, as compared to the probably very complex but not very scalable options like SWITCHR, or pretty scalable like vertical but not very complex. So another dimension here is speed, and SkyTree claims that they can provide up to several orders of magnitude increasing performance with different kind of algorithms. Now our goal for this project was to test this performance increase, and we chose to use the GBM model. First, because it's our tool of choice for various different projects. Second, because it is inherently not a reliable algorithm, because it works on the residuals of the previous steps, so it's really hard to compare. So we were really interested in how SkyTree can increase GBM model creation without paying any price in terms of the model accuracy. So we want to model accuracy to be so we have several data sets of several different sizes, ranging from 700 megabytes to 420 gigabytes. And as I said, we want to ensure that we have the modeling parameters capable of just the same as displaying RGBM as can be found on RStudio. And we want the quality of created models to be very similar or approximately the same. We use Gini coefficient for classification and MSRI for regression. Also, we wanted to test the scalability by using this huge data set, and the data set that cannot be modeled on a single server. Although we have single servers with 1 terabyte memory size, still it was not able to do with this data. So to work with SkyTree, there are several steps that you need to go through. They're pretty quick and pretty easy, but you need to create the header and you need to transform your data into some proprietary SkyTree format before you create the model. And I will fast forward through these steps. Just highlighting some stuff. For example, if you have the training, test, and validation set, you can create the headers for all of them in one step. Conversion of the data can be done so that some of the data transformation can be used on this step as well, and it's pretty convenient. Yes, and the model, the product as we used it is a Linux-based command line product, although now they have different user interfaces, as I understand, but this is what we tested. And this is the model creation itself, the command for model creation itself. You see that there is opportunity to select different loss functions here. And one really good stuff is that you can provide several parameters, and you can find the best tuning parameter again in one call of the function. It will provide the best tuning models, the best tuning parameters and actually things like variable codes as well. Other than GBM, they can do this type of different models like images, neighbors, forest, and simple vector machines. This is how the scoring looks like. What is interesting is when it is applied to the Hadoop-based in the Hadoop-based environment, you actually don't need to write any MapReduce code. You just write the same kind of command, and instead of providing the data files, you provide the data directories that contain the data. And SkyTree just runs and creates and runs MapReduce skills, which is pretty neat. That was the step of data preparation, and this is actually model creation. So there are several parameters that you need to play with to make this job runnable, and this is actually the results. The results were pretty impressive, so that we actually can got this product, and you can see that the improvement over R can range from 20 times to 88 times, and this range from, for example, from 9 to 20 is explained by the fact that we wanted to we wanted SkyTree to really reproduce the model that created by RGBM, who had the computer accuracy, very accurate. For that, they created different parameters that just reflects the R. For example, the number of splits on the trees. And in this case, the speed up is not that big, but whenever we let SkyTree really fly and a little bit increase our constraints on the quality, and I say this means tens of the percent of difference between the conditions. And on Hadoop, we are the speed up is a little more. Now this test was performed by SkyTree on our database, on a database that was provided by Allstate for the Gabe application a couple of years ago. And the reason for this exercise was to see the dependence of the speed up on the data size and the dependence of the speed up on the model complexity. So here is increasing of the data size on the right hand side. Here is the dependence on the model complexity. And we see that in this case the speed up is a one. Right, so this is the kind of the numbers that we actually get in real kind of reality check test. We really glad with what we see, and we are looking forward to working with them on our side. If you got any questions regarding Allstate, our department, and actually we are hiring. So if you're interested, please come and see me. If you're interested in the product, please ask me.
Yes.
What's the license?
Gabe, you want to come set up?
Sure. What was the license?
What was the license?
The license.
Sorry, the question, what was the license?
Yes, is there a license for it?
Is it commercial or free?
Yes, it's commercial, yes. Yes, it's not free.
If you're very curious, I can answer your questions later.
There are some representatives.
I'm not Dr. Khan.
He's one to know.
Hey, so thanks for coming. I think I'll borrow a trick from DIrk and start my talk with a question. So how many of you have ever seen a published result that's over 4 years old?
Sorry, what was it?
A published result that's over 4 years old. Right, everybody, I'm sure. Now, how many of you have ever tried to recreate a published result that's over 4 years old? That was generated by someone you don't know. It's not easy, right? And part of the reason that it's not easy is that package versions matter a lot. So I recently tried to regenerate some published results from a FileVendor package called DEC. And they provided the session info, they told us exactly what package versions they were using, and those package versions actually did different things than the newer ones. So you end up with radically different results if you can even get it to run, because the API has also changed in the last 4 years. So basically, what this comes down to is if you want reproducibility, if you want to be able to recreate results of others and have others be able to reproduce your results, then you really need to pay a lot more attention to package versions than people typically are, and you need to be able to get specific package versions that are called for in various situations, and that's not super easy in R right now. I'm going to present the SWITCHR package, which I've been working on, which attempts to address that. So, what are some of the specific situations where package versions matter? Reproducing results, as I was just talking about. Also, when you're developing packages, you definitely want to be developing against development versions of all of the dependencies of your package. You don't want to be lagging behind so that as soon as you release, they release a new version and all your code breaks, right? And so you need to have essentially side-by-side libraries, one which you develop against and one which you use in your analysis where you want to be able to test the results. Third, there's collaboration. So if you are working with 10 people around the world and they're all using different versions of packages and even different versions of R, you guys may get different results when you run the same code. And so then how are you supposed to try to come together and get an answer that everyone can agree on if all the versions are different? So that's why we need to care about package versions. The other thing that's important to talk about here is that package versions are sort of hard to find sometimes, right? It used to be that if you wanted to install a package, you go to CRAN, you install whatever version is in CRAN, and then you just use that. But obviously that's not going to work if you need a package that's 4 years old that's been continuously developed since then, because that version isn't going to be on CRAN. There are other versions of packages that have not gone to CRAN yet, right? They are the development versions that they live in GitHub. They live in various package repositories. There's multiples now. There's CRAN, but there's also Bajuk-Yorgan. There's another one called OmegaHack that has some experimental stuff on it. And the old CRAN packages live in CRAN archives, so they're still available, but install that packages can't get them for you. It doesn't understand how to install them because they don't live in a repository. They just live in a directory on a website, which is almost the same as a repository, but it's missing some of the important features. And finally, if you're on GitHub or if you're in Bioconductor SVN, the old versions of the packages actually live in the SCM repository where your code lives. It's just Arc obviously doesn't know how to get at those. So what do we need? We need to install the package versions that are relevant to whatever we're doing. So if we're reproducing a paper, we need to install the package versions that the authors used. If we are collaborating, we need to sort of get together with all our collaborators and decide on a canonical set of packages, and then we'll be able to install them together. And we want to be able to do that without constantly overwriting other things that we already have installed, right? So if you have your sort of production analysis set of packages that you've installed, and that's what you usually run your R code in, but now you want to go and reproduce an old result, and you want to install an old version of Lemma, you'd really like your new, actually good version of Lua to still be there when you're done, so that you can use it. And so really what you need there is side-by-side package libraries. And R has some low-level functionality for this, but it's not super convenient to use. And so one of those things that we're going to see that SWITCHR does is sort of wrap that up in a nice API where you can really easily have these libraries that you can borrow from each other, they can inherit from each other, but they're separate and they don't affect each other's contents unless you want them to. And so we want to be able to use those to recreate other people's environments. So in the case of this bioconductor paper that I had, they had the session info, and I'd like to be able to get all of the packages they use and just install them without all the pain that it ended up actually being to do that. And we'd also like to publish what we used in a way that will allow others to do the same thing very painlessly. So our studio has this PackWrap package which does something like that. But we'll talk a little bit about the differences. But they basically sort of tarball up all of the packages and just sort of email them around or put them on the web or things like that. Whereas we're going to actually describe the contents of your library, and then SWITCHR knows how to actually recreate those. So the short answer is SWITCHR is going to allow you to do all of these things. And the way that it's going to do that is with what we're calling package manifests. So what a package manifest essentially is a generalized, decentralized package repository. So it's a list of package names and associated information that's going to allow SWITCHR to install those packages. And really that's all you need. So basically what that comes down to is where does the source code live, what sort of program is going to need to use to get the source code back out. So it's in the Git repository, it needs to know that it has to use Git, SVN, if it's just on the web, you can just download it, things of that nature. And then optionally you can sort of say, my manifest is only going to include certain versions of these packages. And so finally, in the last bit of my lightning talk here, this is a showcase of the API. So this is how you would actually do these things in SWITCHR. So the first and simplest thing that you might want to do in SWITCHR is create a new SWITCHR library. Basically, this is all going to happen with this switch to function. And what that does is it's going to say, okay, you're asking to switch to this library called mynewlib. It will check whether that exists or not. If it does, you switch so that your session will load and use packages that live there. If not, it will actually create it automatically and put it into a place where it will know how to find it again next time you ask to switch to it. And you can see it gives you some information about the library that you just switched to. You've got 29 packages available. In this case, this is empty, so those are all going to be the basic recommended packages. And you can see that one of the options that you can have is you can suppress or not suppress the site library on the current system that you're on. So sometimes you have a site library, and those are the packages that you generally use in production. But again, if you need 4-year-old packages, you don't want the current versions of its dependencies mucking everything up when you try to load them. So you can tell SWITCHR, no, when I'm in this library, ignore the site library, take it out of the search path, and don't find it. And then you can see it has a little note there. If I get back, just switch back, and then everything will be as it was before switched. So this just illustrates that. So in this particular case, I was in the recreate video environment before I ran this. So I switched back to that, and then you can switch to it again, and that's basically switching back and forth. So that's all well and good, but that's not really the interesting bit. The interesting bit is these manifests. So how do you create a manifest? Well, there are some helper functions. So if you have a manifest that has a bunch of GitHub packages on it, you call the GitHub manifest, and you give it username repository, and it knows what the rest of the GitHub URL looks like, so it just slaps those on there for you. And you can see that now we have a manifest that has these 3 packages. It says it also has 5 dependency repositories, so those are where it will look for dependencies that it doesn't see listed in the manifest. Typically that's Crane and Bioconductor, and some specified other ones. And so how do you install from a manifest? The output is omitted because, as we all know, installation of our packages is verbose and generates lots and lots of output that wouldn't fit on the slide. But you can see that after I run this, if you run installed packages, you can see that our catch which is a package that I've written, and all of its dependencies, which are codepends, fast digest, and XML, were all installed during this call. And so that's actually subtle but important, that SWITCHR will find the dependencies when you install from a manifest. And so what it's actually doing behind the scenes is it's creating a just-in-time repository. So it's constructing a repository that contains only the package you wanted and all of its dependencies locally, and then using installed packages from that. And so you actually get, I didn't create any of the actual installment. It all goes down into the core R package installation mechanism. So there's no duplication of work there. And so that's good. We can get packages into our library. So how do we get a manifest that describes our library, which is how we're going to sort of publish and communicate what we've been doing. So that's the lib manifest function. You can see this is called a CD manifest for a reason that we'll see in just a second. And this is basically a package manifest with additional filters on it that specify exact versions. And so we can see we have these 4 packages that are installed. It does not include the base packages by default because they're not installed in the directory. They're installed wherever R is installed. And you can see that it knows both where the packages and versions. And actually, it doesn't print this because it would not fit anywhere. But it actually also knows where to get those packages. It knows where they were installed from. So the install mechanism actually gives provenance information about where it got all the packages it's installing, and you use that to recreate the manifest. So the final thing, well, almost the final thing is, so we can go from we can install from a manifest, we can go from a library to a manifest, we can also go from a manifest to a library, and that's with the seeding mechanism. So if you create a new library, you can actually seed it with a manifest, and it will install all of the packages the exact versions of the packages that are listed in that manifest, and then you're just good to go. So basically, if you have a manifest for a paper, you call this, and then you just source the R code that generates the results in the paper, and you should be done, unless there's something geeky going on. This is another package that I sort of put together based on a GitHub package by Carl Schreiber, I think, and this will actually publish a manifest into a GitHub just with that line of code there. So final example here is you can actually generate a manifest that corresponds to a previous version of R, and it will have the exact versions of everything that was in CRAN at that time. And then if you're installing from that, it's as if you're installing from CRAN as it existed when that version of R was released. And so that is going to point that will point to CRAN archive for old versions, and for versions that are up to date, it knows that it has to go to the actual repository because they don't go to the archive until after they're superseded. And that is the SWITCHR package. These are both available freely on GitHub, they're open source. So yeah, that's it.
Lewis, last but not least.
I was a little confused about your nomenclature. When you originally started talking about creating a new library, you had an example of the switch command, but it looked like that was switching to some existing library that you have already created.
No. It looks the same either way. So if it doesn't exist, it creates it and then switches to it. So it was empty, which is the 29 packages that were in there, those were all the base packages that come with R. There was nothing other than R in there until after you installed into it.
Okay, I'd like to ask the speakers if you want to mail me your slides or any links, and I'll make sure they get up on our meetup page.
My name is Bajuk. I'm going to be talking about real-time applications using the R language. In particular, using a couple of offerings from TIFCO software. So the first question I often get is why? Why would you use the R language in real-time applications? This audience might not be as skeptical of that, but in general, there's two reasons. On the one hand, you want to have the full breadth of analytics that you get in R. So that, as with any application, you want to have a wide choice of models so you can find the best model to solve a given problem. But another important point is the ease of prototyping and new analysis, so that someone who's deploying some analysis out in real time can rapidly respond to changing opportunities and threats. This was really brought home to me by a particular customer who was doing fraud detection, and the fraud was an evolving threat in that they had an online store where they had to deal with fraudulent transactions. As they rolled out different models, the people committing fraud would react to what transactions were getting canceled. Therefore, they would then change their behavior, and this company would then have to roll out new models. So they have to iterate fairly rapidly and have a smooth way of doing that. The challenge, of course, is to run R language analytics quickly enough that you can apply them in a real-time environment, and enable this quick cycling of rapid prototyping to production. We use a couple of components to do that. TIFCO, one of our really core businesses, has been around complex event processing. You'll often hear TIFCO talk about fast data, contrary to a lot of marketing messages we hear about there around big data. Fast data all about dealing with the large volumes of data coming into organizations and how do you react to that data fast enough to make decisions. We've got a couple of different products, TIFCO Streambase and TIFCO Business Events, that deal with complex event processing. And secondly, we offer TIFCO Enterprise Runtime for R, or TIR for short, which is an alternative interpreter for the R language that we developed from the ground up based on our long-term expertise with S+. Something that's generally more efficient and faster than the open source R engine, and something that's freely available to the R community. At the end of my talk, I'll share a link to that, but I want to emphasize that this is something that anyone in the R community can use, download, and freely get benefits of. Our focus as a commercial provider here is we want to provide TIR for embedding in platforms. We embed it in our own platform, SWITCHR, which is our data discovery and visualization environment, in our complex event processing products, and also we embed it in partner products. On the development side, we're compatible with RStudio, so you can use the same capabilities in RStudio that you develop on top of the open source R engine on top of TIR. So in general, the idea is to apply the R language in real-time analytics environments to fast data. And so that when some event is triggered within this data stream, an analysis using the R language is applied. This way, an automated business process might make a decision to extend an offer to a mobile customer or stop a fraudulent transaction, or might pull in SWITCHR to provide some visualization around the context of the event that's happening, allowing someone to make a live decision rather than a real-time decision. We've got many different use cases that we've used this in. This is one of my favorite. This was working with a logistics company in the Far East, and they wanted to do some logistics optimization. So there's a couple of different applications where TIR is being used in production, where R language analytics are being used to basically make this logistics shipping business better. One is port congestion detection. As the ship is some distance away from port, checking the congestion in that port, applying some simple models to determine how likely is it that there's going to be a berth available when the ship comes in. If it looks like it's a high probability of not being available, then the operator gets signal in order to slow down the ship so that they don't have to pay high waiting costs on the way. Another one is marine time abnormality detection, which is detecting when a ship is likely to deviate significantly from its designated sailing path. And so once this designation, once this likelihood is calculated above a certain threshold, the carrier and the operator of the ship are alerted. And so in both these cases, we're using the real-time system as the framework, but the core of the analytics is being used in real-time, is being used in the R language using DIrk as a platform. We also do quite a bit in the oil and gas industry, and their predictive maintenance is very important. So minimizing downtime of oil and gas equipment, where engineers can track sensor data, and based on that, and applying models in the R language on top of DIrk, basically determine whether or not equipment is likely to fail, when it's likely to need maintenance. And in the past, this was usually some ad hoc rules, but by doing more sophisticated predictive analytics, they can minimize unplanned downtime and really plan their maintenance much more efficiently. Severe weather alerts for facilities is another area where we use this, where it's combining several different bits of technology in R, using the SP and RGL packages to compare areas of where weather alerts pop up, such as a storm warning or tornado warning, comparing that to the physical location of the facility. And if it looks like there's an overlap there, to alert the managers of that facility to take appropriate action. And using Spotfire in terms of visualization, you can map that information from the Spotfire environment as well. Customer loyalty analytics is something we do quite a bit at TIFCO. This is delivering real-time predictions on whether or not an offer should be extended to a given customer. And so this allows you to do things like best marketing offer, predicting customer churn, how to generally optimize your offers to a given customer. And again, the idea here is by using the R language within a flexible framework, you can very rapidly iterate and develop new models and roll them out to change, respond to changing opportunities and threats in the environment. And so I know at this point I'm the one who's keeping you from going home, so I'm going to keep it short. And I just wanted to summarize that a fast R language engine in a complex event processing real-time platform enables broad access to the right R analytics, so that you can have the best chance of finding the best model, the most efficient model for doing data prediction, and allows someone to really rapidly iterate and respond to changing conditions. Typical enterprise runtime for R is our answer to this. Again, this is a brand new, a couple years now, an alternative interpreter for the R language that we built. It's embeddable in commercial applications. We use it in a number of different typical platforms. But it's also freely available for our users at tap.tifco.com. I encourage you to download it, load it up in our studio, and you can basically get some of the memory efficiency and performance benefits of DIrk using the same R code that you'll be using from R. Support for this version is through our community site, tifcommunity.com. And so if you'd like more information, you can visit either of those sites or spotlight.tifco.com/chair or drop me. Thank you.
So we have a few minutes to take questions for any of the speakers that are still here, and I think everybody is. Any questions? See you next time then.